Good morning, sir.
Good morning, everybody.
Good morning, sir.
Good morning, sir.
Good morning, sir.
How are you all?
Fine, sir.
Good.
Fine, sir.
Stay safe and healthy. Well, just wait a couple more minutes. There's some students join this class from another class. Okay.
Sure, sir. Thank you, sir.
How many have joined? Can you see that?
Sir, around 40.
Okay. Let's wait a couple more minutes because we have 76. So half joined, almost. Little more than half. Okay. How many have joined?
53.
Huh? 56.
53.
53.
Yes, sir.
Okay. Any question from last class? Anybody has any question? Okay, last class we ended with the concept of edge dislocation. First we talked about what is a dislocation. Dislocation is a region of localized lattice disturbance separating the slip region from yet to be slip region or unslip region. Here we showed you a model, the surface A, B, C, D, above which the crystal moved by one atomic distance with respect to the area at the left. So the boundary between slip region and yet to be slip region is AD, and that is the region of localized lattice disturbance, which is called an edge dislocation. So in picture, if you magnify, I'll come back. If you look at from this direction, if you are looking from this direction, say you are looking from this direction. I don't know why these things are coming. I'll get a view like this, atomic level view. There is an extra half plane lying over the slip plane. The slip plane is somewhere there. Slip planes means on which this dislocation line exists and it moves along that plane. That is called a slip plane. It's a crystallographic plane. So extra half plane lies above this slip plane which I drew. Is a atomic plane. And what I showed you is this. Around this dislocation, if I look it from the top, the plan view will be a line for this extra half plane. And the plane, the immediate vicinity, like this plane, that plane, this plane, and so on, will be distorted. Means the atoms from their equilibrium position gets moved towards this, moves away. In the top portion of the slip plane, bottom portion moves towards the dislocation. So they are distorted with respect to their equilibrium position. So this region, few atom spacing region around the dislocation line is distorted. And this is the region of localized lattice disturbance. I repeat, region of localized lattice disturbance, separating the slip region from yet to be slip region. If I look at from the top, it looks like a plan view. The extra half plane appears to be an edge of a knife. So this dislocation is called an edge dislocation. That's all I said in the last class towards the end. Any question? So same thing I'm showing you again. This is a perfect lattice. Okay, these are lattice points and you can assign an atom to the lattice point. This is a perfect one. And SP is the slip plane. Slip plane. For example, in hexagonal close pack, 0001 plane is a slip plane. For face-centered cubic, 111 plane is a slip plane. Later on you will see why slip takes place in those planes, because those planes are of the highest atomic density. It is easier to slip on those planes. And you see, when I talked about crystallography, the stacking sequence of 0001 plane in HCP, AB, 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 AB. Similarly, the stacking sequence of 111 plane is ABC, ABC, ABC in face-centered cubic. And this atomic density, the arrangement of atoms on those planes for those two crystal structures are identical. And slip takes place on those highest atomic density plane and in the close pack direction. And close pack direction in HCP will be 11 but to 0 direction, and face-centered cubic will be 110 tight direction. Now in this perfect lattice, if I insert one extra half plane, this one is highlighted portion. The bottom is missing. Thus, there is in terminology called one extra half plane above the slip plane. And if I have a ball and stick models, this area looks like this. So there is an edge dislocation present on the slip plane. Yes, please. Just a minute. Just a minute.
Okay.
Yes, please.
Yes, so why is it called edge dislocation? Edge.
Because a knife edge is there. So if you look from the top, the plan view is like line and it's like a knife edge. So the terminology edge dislocation came. EDGE, edge dislocation. You must have a copy of Dieter's book. Chapter 4, 5, and 6 are essential for this section. Now, this is another picture of this, how you insert an extra half plane, it becomes an edge dislocation. Now the attempt will be made, can I quantify an edge dislocation? Somehow, mathematically, can I quantify an edge dislocation? You see this picture. This is a perfect crystal. No defect is there. Let's assume one atom randomly and start a circuit from there. 1, 2, 3, 4. Randomly I chose 4 atom spacing down from that red color atom. Then from left to right I move 1, 2, 3, 4, 5, 6. It can be 7, it can be 4, it doesn't matter. Now I came down by 4 atom spacing. I go up by the same number. 1, 2, 3, 4. That has to be fixed. The number of atom spacing I came down, I have to go up by the same. And how many I moved from here? 1, 2, 3, 4, 5, 6. So from this point, I'll move by the same atom spacing. 1, 2, 3, 4, 5, 6. So I started at the red color atom, drew a circuit, and ended up at the red color atom. The start and end points are identical. Now look at the right side figure. There is an extra half plane. There is an extra half plane. Okay. So now we are drawing a circuit around it. 1, 2, 3, 4. Move here 1, 2, 3, 4, 5 spacing. Came down by 4, moved by 5 from left to right. Go up by 4. 1, 2, 3, 4. And now you have to move 5 spacing from right to left. Because we moved by 5 spacing here. 1, 2, 3, 4, 5 from left to right. So at this point from right to left, I move by 5 spacing. 1, 2, 3, 4, 5. Now where do I end? Not on this green color atom, on the red color atoms. The circuit is not complete. So now if I draw a vector from end point to the start point, if I draw a vector from end point towards the start point, from end towards the start, it has a magnitude, this atom spacing here, and it has a direction. Direction from where? From red color atoms to the green color atoms. So a vector is defined by 2 things, its direction and the magnitude. And this vector is called Burgers vector. Burgers vector. This vector is called Burgers vector. The circuit I drew is called Burgers circuit. Burgers, not Barger. Burgers vector. There is no apostrophe. This is the surname of a scientist. The closure failure is the Burger's vector. Magnitude is this atom spacing, direction from end to start towards that direction. So this extra half plane edge dislocation now is quantitatively defined by its Burger's vector. Any question? How many students are in the class now?
Sir, 75.
75. Sir,
Yes. Please. Any question? Now you look at, we want to find out if you have a dislocation, what happens to the crystal. You see here, you have an extra half plane lying on this slip plane. So when you have an extra half plane, it tries to push the atoms towards the left, towards the right, because I inserted one extra half plane. Assume you have a bucket of water. You add a drop of water to that bucket. Can you measure the change in the height of the water level in the bucket? One drop of water in a bucket full of water.
no, sir.
Why?
It's very negligible.
Relative
Because surface tension forces is holding the shape or top of the top of that water level. Similarly, if I insert one extra half plane, it tries to push the atoms apart in the top half of the slip plane. This is my slip plane. Okay. But to maintain the continuity of the geometry of that solid, the solid applies a force or stress towards this extra half plane. What type of stress is this?
compressive.
Yes, it is a compressive stress, because this extra half plane is trying to bulge the solid crystal outwards to maintain the geometrical integrity of that solid, no change in shape. A compressive stress is applied on that. Now there is no atom in the bottom of the extra half plane. So the atomic planes, continuous atomic planes, will try to collapse towards this open space. Similarly, to maintain the geometrical integrity of that solid, stress will be applied to the crystal outwards. So what will be this stress? What type of stress is this? Tensile stress is pulling it apart. This is tensile stress, this is compressive stress. So one thing is clear, when you have a dislocation, it will be associated with a stress value. And when you have a stress, what do you have with that?
Strain.
Strain.
I didn't hear you. Loud, please.
Strain.
Strain or energy.
Yes.
Strain is manifested will be in terms of energy. So the presence of dislocation in a system increases its energy. There is another type of dislocation which is called screw dislocation, or older books it is written as Burgers dislocation, because Burgers is the person who proposed this concept. Remember, all this concept came in the 40s, last century, beginning of last century, where you see this similar picture I showed you for edge dislocation. When edge dislocation, line AD above which there was an extra half plane. But in this case, in this geometry, around this AD line, there is no extra half plane. Rather, you have atoms lying on an imaginary spiral. How many of you have a spiral notebook with you right now?
I have, sir.
Have a spiral notebook. Through the spiral, through the center, along the axis of this spiral, put a pencil or pen in. That's your dislocation line, that pencil or pen. And on the surface of that spiral, you have the atoms lying there, and they are off from their equilibrium position. So the atoms are arranged like an imaginary, lying on an imaginary spiral. Some below, some on the page of the paper, some above the plane of the paper. So this red color thing is the imaginary line around which the atoms are lying on an imaginary spiral. Portion of the spiral behind the plane of this paper, portion is on the paper, portion is at the top of that paper. So this entire region will be the localized lattice disturbance. This is the width of this dislocation. So the width of this, the diameter of this spiral is your localized lattice disturbance region. Am I clear? So this is the picture.
There must be some driving force for this kind of dislocations.
Of course, wait. The energetics will come to it. Under equilibrium condition, well annealed, well heated sample has 10 to the power 6 dislocation lines per centimeter square. Heavily deformed has 10 to the power 12 lines per centimeter square. Below 10 to the power 6, if you want to remove dislocation, it becomes difficult and you have to, thermodynamically that is not stable. So defect-free crystals is very difficult to create. So in this picture you will see there's an imaginary line AB around which the atoms are arranged or as if on a imaginary spiral. So this is the width. This is the width of the screw dislocation. If you look at a metal screw, the threads of a screw threads of a screw is basically a spiral. So if you put atoms on the thread of a screw, metallic screw, you get the same arrangement like what we are proposing. So these dislocations are called a screw dislocation. A screw dislocation. I'll skip few slides, it's not required. It will be taught in details next semester in mechanical metallurgy class. Any questions so far? Anybody? You see the top half of the schematics are for edge dislocations. You have a step because the dislocation line, edge dislocation is formed. This region is slipped, region beyond is yet to be slipped. So this is the boundary between a slipped region and unslipped region. With the application of shear stresses, the dislocation moves on the slip plane from this end to the other end. It is moving like that. This dislocation has a vector and the magnitude of the vector is its Burgers vector. Length, that's one atom spacing, lying on that slip plane towards the slip direction. This is the slip direction. So when the dislocation line reaches the end of the crystal, it creates an offset. You take a deck of cards, push few cards, slides few curves with respect to the rest of the card, they will create an offset. So the magnitude of this offset will be same as one Burgers vector magnitude. So if you move 10 dislocation, edge dislocation along the slip plane, and all of them reaches the end of that crystal, the amount of offset created will be 10 times his Burgers vector. If you move 1000 dislocation, edge dislocations, his magnitude will be 1000 times the Burgers vector. So this is the slip plane on which dislocation moves or glides. Same thing, or slips. This is slip plane, this is slip direction, and this entire phenomena is called slip. Now the same crystal, I formed a screw dislocation. And by the application of shear stresses, screw dislocation moves from right to left. Here, front to back edge, here, right to left. When the screw dislocation reaches the end, you create an offset. You see, this portion, the second and third figure, is different than the second and third for edge. But the last figure, when the screw dislocation reaches the end, or an edge dislocation reaches the end of the sample, it creates an offset. Identical. There is no difference in their appearance. And the magnitude of that offset is equivalent to their Burgers vector. So the slip created by an edge dislocation and edge dislocation, the permanent offset created by them, are identical. So there is a summary here. Dislocation property for edge and screw. Relationship between dislocation line and Burgers vector. In the case of edge dislocation, it is perpendicular. You see, this is edge dislocation. The slip direction of the Burgers vector is lying perpendicular to it. Here, it is parallel. For screw, it is parallel. Burgers vector is parallel to each other. Slip direction for edge, parallel to the Burgers vector. In direction you are having slip. Same case for screw dislocation, parallel to the Burgers vector. Direction of dislocation line movement relative to the Burgers vector or slip direction, same thing, it will be identical. In edge it is parallel, but in case of screw, it is perpendicular. And how dislocation moves from one slip plane to another slip plane, I'll explain it later, but write it down in this case. For edge dislocation by climb, for screw dislocation by cross slip. What is the slip plane of face-centered cubic?
One, one,
One,
one.
one, one.
One.
So in a face-centered cubic, how many 1-1-1 type planes are there? How many?
Four.
Where the 4 different ones? Can a dislocation move during slip from one 1-1-1 type plane to another intersecting 1-1-1 plane? Anybody? Look, I am not giving you assignment or homework because of your tremendous study load. But I expect that you should read a little bit. I can be flexible to a great extent. But if you take advantage of that and do not study anything at all, then I feel sad. Do you like that every class I'll give you an assignment, you have to submit it in the next day or so? So when I request you, please study. At least I expect that you will respect my request. Along which direction 111 type planes intersect? Huh? You see 70 plus students, not a single fellow answered it. Two intersecting 111 planes, type planes, along which type direction they intersect? I will not give you the answer anymore for this. For each dislocation, Burgers vector is perpendicular to the dislocation line. What does it signify? Dislocation line and is Burgers vector perpendicular to it. So it defines a surface. So when an edge dislocation glides on a 111 type plane and comes near another intersecting 111 plane, it cannot move from one slip plane to another. The reason is two planes intersect along a line, and edge dislocation defines a surface because its Burgers vector is perpendicular to its line. A surface, a two-dimensional surface, cannot be accommodated on a one-dimensional line. Hence, Burgers vector cannot, hence edge dislocation cannot cross slip from one slip plane to another slip plane. Can it move from one slip plane to another slip plane? Any other means? If the slip planes are parallel to each other. Switch off the microphone, lot of noise coming. One of you, please switch off your microphone. This is my slip plane. This is another slip plane, parallel slip plane, another slip plane, another slip plane, and so on. So if I remove the entire bottom row of atoms, the edge now does not come down to this level. The plane ends here. So edge dislocation moves up from this slip plane to that slip plane. And this phenomena is called climb, and more particularly climb up. Now if I add a row of atoms at the bottom of this extra half plane, this extra half plane ends at this plane. So that is called climb down. Climb up, climb down. By removing the entire row of atoms, it's called climb up. By adding an extra row of atoms, it's called climb down. And these are the parallel slip planes. So an edge dislocation moves from one slip plane to another slip plane, not by cross slip, but by phenomena called climb. You look at a bookshelf in your home, a brand new bookshelf, all horizontal shelves. You added books on it. With time, the wooden plank will bend downwards, and remove all the books. Still it is bent. So you got a plastic or permanent deformation of that wooden plank. Even though you did not load it significantly at the beginning when the plank got bent, it was horizontal, but with time it bent. And this phenomena is called creep, C-R-E-E-P. Even though loading is below the elastic limit, with time deformation takes place. You say, if you have interest, then every few thousand hours, the jet engine blades are replaced. Fighter planes or domestic planes, because they are operated at a very high temperature. And even though they are not loaded in the plastic regime but elastic regime, but time dependent deformation takes place in them. That is called creep. So before creep becomes significant, the blades are replaced. They are very expensive, but life is a lot more expensive than those jet engines. You cannot put a price tag on life. What happens? Why they creep? Because of this climb of edge dislocation, climb up or climb down. So even though you load it in the plastic regime, elastic regime, it is experiencing plastic deformation as a function of time dependent deformation. That is creep. So edge dislocation cannot cross slip because it defines a surface. It cannot be accommodated along the line of intersection of two slip planes. But it can move from one slip plane to a parallel slip plane by the phenomena of climb. So you have to take a row of atoms out or add a row of atoms. So this movement of atoms is called diffusion. And that is possible if you supply a high temperature, sufficient thermal energy to the atom, so they can move from one vacant site to another vacant site. So creep takes place at relatively high temperature. Any question?
Sir,
Yes.
is there any way to prevent creeps? Like,
No way.
okay, sir.
You can develop certain alloys whose melting point is very high. Diffusivity means the rate of diffusion of atoms in that material is very slow. So you can minimize them. But you cannot remove the creep completely.
Okay, sir.
So generally these engine materials are having very high melting point. Any other question? How many of you have a paper clip or James clip in front of you? Anybody?
Normal sprays that not get.
Huh?
I have paper clip.
Is it plastic coated or just metallic?
It is. I think it is plastic coated.
I don't know how good will that work, but straighten that James clip and twist it back and forth. Fold it and straighten it. And see at the beginning how much force you have to apply, and towards the end, when you snap it, how much force you have to apply to break it. Anybody has seen a blacksmith hitting an iron or steel object and making a knife or a shovel or a digging equipment, anything? How the blacksmith works?
Yes, sir.
You see,
Yes, sir.
red hot
Yes.
condition, they hit it with a hammer, gives a shape. And they cool it in water. You learn why they do it. They know the trade, but they don't know the science. But after it is done, they again, in the cold condition, they beat it with a hammer before they sharpen a knife or something. Did your paper clip snap, break?
No, sir.
Because of plastic coating. If you have a metallic piece, if you twist it, it will snap after several twisting events. Every time you twist it, it generates more and more dislocation. If it is true dislocation, it moves from one slip plane to another intersecting slip plane. Because true dislocation, Burgers vector is parallel to the dislocation line. So it defines a line, not a surface. So when you apply a shear stress, it moves from one slip plane and goes to the intersecting line between two slip planes, and then move to the other slip plane by the application of shear stress. So a screw dislocation can easily cross slip. Okay. But if more and more dislocation or cross slipping, they get entangled on the slip plane. And you have to apply more and more stress to overcome this entanglement. And eventually your sample breaks. You increase the dislocation density to a great extent. So try to do this experiment. Get a metallic paper clip, means no plastic coating on it. Twist back and forth, straighten it up like a wire, twist it back and forth, it snaps. You can take aluminum wire, you can take steel wire, you can take copper wire, you get the same results. So every time you twist, you introduce a lot more dislocations in it. So quite a few of you have a habit.
Sir,
Yes?
sir, it gets heated in the process. I have tried this once. I tried to break a wire, but it didn't break. And when I touched the area, my hand got burned. It was so heat.
Got burnt or?
Sir, it was a thick wire. So I tried it to break by bending and straightening.
Does it have a plastic coating on it?
No, no, sir, a wire. It was an aluminum wire.
You keep on doing it, it will snap.
Yes, sir.
It will snap.
But it gets very much heated in the process.
Yes.
The end, if it is a thick wire.
Now tell me why it got heated.
Yes, sir. I was asking that only.
Every time you twist it, you applied a shear stress to it. You generate more and more dislocation.
Yes, sir.
How dislocation get generated will be taught tomorrow. This dislocation is associated with that energy, and energy is manifested in terms of
Yes, sir.
temperature rise. Right.
Yes, sir. Yes, sir.
That's exactly what is happening.
Okay, sir. Thank you, sir.
So when you started, approximately that aluminum wire, for which purpose you had it with you?
I wanted a smaller piece from it. Was no, sir. For क्या बोलते हैं, for like connecting, for like hanging cloth. It was a big aluminum roll wire, so we have to cut it big piece like 2 feet.
So it already had close to 10 to the power 10 dislocation lines per second. Because larger the number of dislocations, stronger the material will be. So when you are twisting, you increase the dislocation density from 10 to the power 10 lines per second to say per centimeter square to say 10 to the power 12. If you do a little more, it will snap. And easy things to take a metallic paper clip, but no plastic coating on it. You can easily snap it after 8 or 10 twisting. Okay. So
Okay, sir.
when you did that, you increase the dislocation density. So quite a few of you have a habit to tie down tightly the charger for your laptop and your mobile phone, right? You tie the cable around the charger tightly so it will be neat. Or you just dump it on the table as is.
No, sir.
Anybody?
No, sir.
It is made
Second
out
option.
of 99.95% pure copper or higher purity. Any impurity atom stays in the copper is the center for scattering of the free flow for electron. It increases resistivity. Grain boundary and dislocation lines are scattering center for the free flow of electron. Every time you twist and wire, electrical wire, with the charger or anything else, you introduce defects to it. And more defects means resistivity falls down.
Yes.
Take a charger which is brand new and a charger which is old. The portion which gets bent the most, where does it get bent the most?
Sir, where is connected to the block.
Where it is meeting the charger head itself, that it is a transformer, AC-DC converter, right?
Yes. Yes.
That joint area,
Yes, sir.
because that area
Yes,
gets
sir,
bent
yes.
the most, and you see the failure takes place at that junction. I lost so many chargers that way. And touch it when you are charging, provided it is insulated. Insulation is gone, don't charge it. Don't do that. Is it hot compared to the other portion of the cable?
Yes, yes. Yes, sir.
Because the dislocation density is much higher there. So the scattering of electron is much higher and it's heated up. So don't try this experiment if the cable is exposed there. If it is fully insulated, touch it with your finger and see. So next time you try to tie up your loose cables for charger, think twice. You introduce both edge and screw dislocations to it more and more, and your electrical conductivity of your charger will come down significantly. Understood? These are the experiments you should try and do that thing. Do at home. Any question? So things I showed you, both edge and screw dislocation, how they move is different. But the end results create same offset, whether it's an edge or screw. So that's where I shall end today. I shall not start the next portion, which I'll do it tomorrow morning, 11 a.m. But I have 3-4 minutes left. If you have any question, I'll be more than happy to answer. Anybody, any question?
So in one class, you told that HCP is more ductile than FCC structure. So does it have to do with screw dislocation?
You misunderstood me. FCC, face-centered cubic, is lot more ductile than hexagonal close pack.
Yes, sir. Yes, sir.
And when tomorrow I shall talk about slip system. Slip system means number of slip planes multiplied by number of slip directions. That makes the slip system. If the slip system is high, ductility of that material will be high. There are 4 slip planes of face-centered cubic, 111 type. Read it up, tomorrow I'll ask. And each plane has a slip direction, 3 slip direction, 110 direction. So 4 into 3 makes 12. HCP 1 slip plane, 0001. And each slip plane has 3 slip directions, 11 but 20 type direction. So 1 into 3 makes 3 slip system. So FCC 12, HCP 3. So which one will give you more ductility? FCC. Copper is FCC, lot more ductile. You take a piece of zinc, HCP is not ductile at all. But if you make an alloy between copper and zinc, which is called brass, you get both strength and ductility together. But body-centered cubic has a 48 slip system, 48, but it is not as ductile as face-centered cubic. because it doesn't have a high atomic density planes like 111 plane or 0001 plane of HCP, 111 of face-centered qubit. It's not densely packed, it doesn't have a densely packed plane. So even though it has a 48 slip system, none of them is as effective as any slip plane of a centered cubic or hexagonal close pack. So BCC is not ductile. Any question? What happened to me?
Sir, hello, sir. Yes, the page that you are now, sir, the